Good afternoon, students. Let us start the lab class today. From today onwards, we will have a different type of lab setup, which means till now we have been discussing only about the hardwired experiments. Means the experiments which we have been till now meant to actually rig up on the springboard or on the breadboard and then give the physical input. That means till now we have been discussing the experiments which were supposed to be physically performed by connecting the actual components. Of course, in this online mode, we are conducting a lab also in a virtual way. But once you start coming to the college in the offline lab, till now whatever experiments we discussed, you will have to actually connect them up and then verify their functionality. But from now on, in this lab, we are slightly deviating. In the sense, we are slightly going to discuss another method of verification that is called simulation. Can anybody tell me what is the meaning of simulation? There are 17 students now. Can any of you tell me what is the meaning of simulation?
So to know the working virtually.
To know the working virtually. That means in the computer itself, we will pick up the components and we will connect the components as per the circuit diagram. And in the computer itself, we are going to perform its verification. So simulation is the verification of a functionality without actually having the physical devices. Which means we need not have a physical device. Without having a physical device, we are able to verify the functionality using a software called PSpice. You can see it on the screen. I have put the name here on the screen, that is PSpice. This is PSpice. Let me tell you the full form of SPICE. SPICE is simulation program with, let me write with in a small letter. No, simulation program. Let me write this with in a small letter. With integrated circuit emphasis. Let me write it as IC directly. For the shortage of space, I am writing it like this. Okay. Now you know that simulation means we don't have a physical component. Now this is a simulation program, SPICE. Let me change the color and let me underline. You can see this S, then P, then IC, then E. SPICE, simulation program with integrated circuit emphasis. So basically this software or a program called SPICE is a freeware. And as of now, even though it was a freeware, as of now Cadence has purchased it and they have kept the name Spectre inside their tool package. Cadence is the name of a company. They have integrated the SPICE program into their set of software tools. But this PSpice is a freeware. Even students can download, students can install. So me and Prithviraj sir have been thinking, and we have been discussing also, that from next class onwards, those who have laptop at home or desktop at home, you better download this PSpice and install within this week itself. And using that installed software, you can simulate these programs even at home. That means you don't have to wait until our offline lab classes start. You can practice on your own. It is a freeware that is available. Student version is available. When the student version is available, you can work out on it. We will be guiding you about how to work on PSpice gradually, but it is better that you download PSpice and install, and you can start working it out on your own way also. It is a quite simple software. It is not very complicated. Today I am going to show you the procedures for working with PSpice. So Spice became PSpice. There are many variants of Spice called PSpice and HSpice. HSpice is again an industry standard software, whereas PSpice is a general purpose software. PSpice is also industry standard only, but HSpice has become more standard than PSpice. PSpice is especially useful for students. So here, simulation program with integrated circuit emphasis. The meaning of simulation is verification of the functionality without having physical device. Now this is a program, that means it is a software, it's a computer program. And it is with IC emphasis, integrated circuit emphasis. Means, what is the meaning of integrated circuit? A circuit which is integrated or packed onto a small silicon chip. For example, the regular pen drive which you are going to use, or the USB thumb drive which you are going to use, it is such a small device, but it is having a silicon chip inside, and that silicon chip internally contains millions of transistors, because of which your pen drive can have a 4 GB memory capacity, 8 GB memory capacity, 16 GB, 32 GB, that way it goes on. Think about 32 gigabytes of memory or 64 gigabytes of memory. 64 into 10 power 9 into 8, because 1 byte is 8 bits. 64 into 10 power 9 into 8, those many transistors have to be present in your thumb drive there. It is true, transistors are so small, they are packed inside the silicon chip, or they are fabricated on the surface of a silicon chip. That is called integrated circuit. Now this particular program can help simulate the circuits which are meant for integrated circuits also. That means generally integrated circuits work with the high speed, high memory, and all such circuits can be simulated using PSpice. That is why it is told as, not only PSpice, Spice as such. So it is told as simulation program with integrated circuit emphasis. Now, can anyone tell me that if there is no physical device, how simulation is possible? When there is no physical device, you will pick up the components from the library of the program. It is basically a software or a computer program. You will go to the menu, there will be a regular pull down menu. As soon as you open PSpice, you will have a regular pull down menu along with a blank screen. Using the pull down menu, you will pick up whichever components you want to connect. It may be passive components, it may be active components. You will pick them up, you will place them on your screen, then you will connect them through wires. And just like you are giving an input signal source in the lab, you are going to give an input signal source even to the simulator. Then you will connect the two output probes for measuring the output. In the physical conduction, you will connect the oscilloscope directly. But even in PSpice, you can connect the scope there at the output, and it can plot the waveform for you. All that is possible using PSpice. My question is, when there are no physical devices there, you are picking up only the symbols from the library. That means, how it can simulate without having the physical devices? That is my question. For example, the same RC coupled amplifier can be simulated in PSpice also. The same Hartley-Colpitts oscillators, or the Wien bridge or RC phase shift oscillator, that can also be simulated using PSpice. But now my question is, when there are no physical devices, what is this program using to simulate the circuit? Can anybody tell me?
So will it use the formulas that is, encoded within it?
Yeah, formula in the sense, in the theory class, we have already seen how a BJT can be modeled using small RE or using hybrid parameters. Now the SPICE will have a bigger mathematical model of all the devices, and it will have matrices inside. Actually, all the simulation programs perform a lot of matrix computations, which means the property or the characteristics of the device is stored, even though we mention it as equations, all those equations are stored in the form of matrices. And whenever you pick up a transistor, its complete characteristic is stored. That characteristic is by means of its equivalent circuit. That equivalent circuit can be either through RE model or through hybrid model. So that mathematical model, in the theory class we have discussed only the primitive model or the simpler model. But there are engineers and scientists who develop very accurate mathematical model for every device. Now, for resistor, it is quite easy. It is simply going to follow the Ohm's law. So based on the value which you give, the computer software will not have a lot of work. It will simply apply that Ohm's law slope. I is equal to V by R. So that way it is basically a slope, mathematical slope. That way it will apply for a resistor. Even for a capacitor, it is not really very tough. X equals 1 over 2 pi Fc. That is the formula which is going to be applied by the simulator. Here the simulator is PSpice itself. But when it comes to BJT or FET, they are non-linear devices. When they are non-linear devices, their complete mathematical model has to be stored in the matrix. And when we plot or when we simulate the circuit, when we plot x-axis versus y-axis, it is going to take all those values by using those matrices, and then it is going to plot the outcome of the matrix computations as the output response. So it is a virtual verification of the circuit itself. That way PSpice is quite useful. Now my next question is, if PSpice is there, then why do we go for hardware experiment? Till now we were doing hardware experiment. If let us say PSpice is there, for every student PSpice only itself can be taught. Why do we require hardware experiment? Can anybody tell me?
Sir, because practically there will be a little bit different values, or the output will be different.
Yeah. Hardware experiment is completely accurate. In the sense, when we actually connect the circuit and when we connect the input and when we measure the output, that is completely accurate. But in PSpice, there is only a library. In the library, there are characteristics saved as equations, as matrices. So, in the modeling, if there is any error, that will be resulting an error in the simulation also, which means the model is very important here. If the model is accurate, then only the output will be accurate. That means the accuracy of the output depends on the accuracy of the model. That is the limitation with simulation. Now, if that is the case, why do we go for simulation? Why don't we use everything hardwired only? That is the next question. We will have to physically verify all circuits. Why do we go for simulation?
Because we can do trial or error in this.
Trial and error. That is one answer. But the answer is, what is integrated circuit? Integrated circuit is having many transistors inside it. Now in the physical lab, let us say if you have to connect 50 transistors or 100 transistors, that is not easy. Integrated circuit will contain millions of transistors, isn't it? I just gave you an example of pen drive, which will contain millions of transistors. So, when there are circuits containing many transistors as such, not one or two, thousands, lakhs, crores, how do we physically connect all those transistors and how do we simulate? It is impossible. Even if we try to connect 1000 transistors in the lab, by the time we connect 1000 transistors, how much time will be taken? And if at all we make connections we make mistakes during the connections, how do we verify? Because if it is only one or two transistors, we can easily connect. How do we connect 1000 transistors? It's a very difficult job. That is where computer is helping us. In fact, integrated circuits came into existence after all these automation processes started. Automation in the sense, without much of human work, if machines keep working, that is automation. Everything is automatically being done. So we need simulation software for one main purpose. When there are more number of transistors, more number of devices, it is not possible by a human being to connect them and verify them. Human being may also make some errors during connections. Think about only 20 transistors, let us say, can we connect using wires on the PCB? Is it so easy? No. That is why this program is with IC emphasis, with the integrated circuit emphasis, means whatever circuits are going to be manufactured by means of integrated circuit technology, all those circuits can be simulated using PSpice. That is the idea. When you come to third year, in the 5th semester, you have a lab called VLSI lab. There you are going to work with one more software called Cadence. That is also a simulation program, but that is going to work both for digital as well as analog. Now, in the case of PSpice, it is mainly analog circuitry, means circuit you have to connect, picking up the devices, and you have to simulate. Digital circuits also can be connected here and it can be simulated. But for digital circuits, later on, when you come to the 4th semester, you will learn a programming language called Verilog and VHDL. Because it is easy to write programs for all digital circuits directly, because they have only two states, 0 and 1. So for that matter, we are going to automate the digital design by using a programming language called Verilog and VHDL, which you will study in the 4th semester. In the 5th semester, you are going to work with the software called Cadence, where you are going to use that software for both analog as well as digital designs, because in Cadence, this is also possible. What Verilog coding, VHDL coding is also possible, and in Cadence, analog simulation is also possible. But in PSpice, it is only the circuit simulation. There is no coding here. Okay. Now the advantage is it has got a student version. You can download, you can install, you can work on it. Okay. This is my introduction about PSpice. If students have any questions, you can ask me, or else I will proceed further. If students have any questions, you can ask me. Okay, there are no questions. Let me proceed. General instruction to work on PSpice. Start up with the capture student icon. This is for the student version software. Then you will have a pull down menu. On file menu, select a new project. Whenever we start working with the simulation, in general, we call it as project. You have to remember this. We don't call it as a circuit. We call it as a project because it may be a circuit, it may be a code in future also. So on file menu, select new project. You can give a project name. Now today's experiment is basically multipliers. So you can give a project name. Now select analog or mixed designs. What is this analog or mixed? Analog means pure analog functionality. Mixed means analog with digital functionality. That is called mixed signal design. Now you have to select this under creating blank project. Now new project is opened. Later on, you can go to the place menu. These are all pull down menus that are available in the software, just like any other computer software. This is also a regular software. Only thing is it is meant for electronics. Go to place. Place means picking the part and placing on the screen. Here place does not mean it is a noun. It is a verb here. Placing the component or placing the part. Go to the place on the menu and select part to get the components. Once you select part, the software will show you the components that are available. BJT is available, NP and PNP is available, resistors, capacitors. In capacitors again, ceramic, electrolytic, they are all available. Now you can simply pick that part and you can place it on the workspace. Once you open this software, you will have a blank screen. That blank screen itself is the workspace. There you can place all these components one by one. Wherever you want, you can place them. And then you can make appropriate connections by connecting them through wires. It is simply dragging and then double clicking. Using the mouse only, all the connections are possible. Almost every action is possible only through mouse here. So this is the initial instruction. Now after the connections are done, you have to simulate the schematic now. For simulating the schematic, you have to go to PSpice menu and select a new simulation profile. In the new simulation profile, for today's experiment, you are going to have a simulation called Transient Analysis. Now, I have a question again to students. Let us say my x-axis is time and let us say y-axis is output. This is one. Let us say x-axis is frequency. Let us say y-axis is output. Now, in the curve which I have shown on the top, what are you going to see here? And the curve which I am showing at the bottom, what are you going to see here? Can anyone tell me? What are we going to see when the x-axis is time? What are we going to see when the x-axis is frequency? Let us consider the RC coupled amplifier itself. In the case of RC coupled amplifier, what are we going to see if the x-axis is time and what are we going to see if the x-axis is frequency? No answer? Okay. If the x-axis is time, you are going to see a waveform like this. Okay. And if the x-axis is frequency, you are going to see a curve like this. That means when the x-axis is time, we are going to plot the output with respect to time. When you are going to plot the output with respect to time, output is going to be a sine wave in the case of a amplifier or an oscillator. I gave an example of RC coupled amplifier itself. So output of an amplifier is a sine wave. So that you can see that sine wave only on the screen. But if the x-axis is frequency, then it means it is the frequency response of the amplifier. At the lower frequency, we will have reduced gain. Then we have a mid-band gain. Then again at the higher frequency, gain is going to become lesser. So if the x-axis is frequency, you will get a frequency response. So in such cases, this particular simulation is called transient analysis. X-axis is time and y-axis is output. That is called transient analysis. That is why the name trans here. Transient means what in general? In general, transient means related to time, related to instantaneous time. In general, when we say transients, we generally mean the sudden circuit functionalities, the sudden signals which are going to appear. In general, transient behavior basically means instantaneous behavior with respect to time. So that way, if the x-axis is time, you are going to see the waveform on the screen, and that is called as transient analysis. That is the transient simulation. Now, if the x-axis is frequency, you are going to see the frequency response of the circuit. Now, this is called as AC analysis, because later on we will have AC analysis also. Upper one is called transient analysis, the lower one is called AC analysis. Now, if at all the x-axis is input and y-axis is output, then you will see the transfer curve of the circuit, output versus input. And then that is called as DC analysis. Anyway, in the third semester, you are not going to perform any DC analysis as such, but you are going to perform transient analysis and AC analysis. For today's experiment, you are going to perform only transient analysis. So, in the resulting dialog box, give it a name, for example, transient. In the resulting simulation settings, give the settings appropriately, in the sense, for how many seconds or for how many milliseconds you want to run the simulation. That is your choice now. Because simulation cannot run for infinite time. When we fix up the x-axis, we tell the simulator tool that simulate it for 10 seconds or 20 seconds and show me the output. Whereas in the real offline lab, you will be seeing the output as long as you connect the oscilloscope to the output. Permanent is going to show the output, because oscilloscope is a real equipment. Whereas here, in PSpice program, there is no real equipment at all. There is no oscilloscope at all. Oscilloscope scope also is there, but that is again a model. So we have to tell PSpice itself that for how much time we want to see the waveform. In the sense, you can keep seeing the waveform permanently, but for how much time it wants to plot the waveform on the x-axis. That is the simulation setting. So, if you give the settings appropriately, then you can save the simulation profile and you can simply click the play button. There will be always a play button. Generally, the play button is like a triangle, filled triangle like this. Generally, a play button is like this. Even on your DVD player or anywhere, even in your mobile phone, you can keep seeing such symbol. This symbol indicates it is play. Generally, it is green. Similarly, if you have this symbol, it is called pause button. You know all these meanings of these buttons. Whenever you have this triangle, filled triangle, that is play. Whenever you have this double vertical line, that is pause. Similarly, you will have many other symbols for stop also, for fast forward, reverse, for all those things you have. Anyhow, here we are going to save the simulation profile and we are going to play. Once you play, the PSpice software is going to simply plot the output response, means output waveform. If it is a transient analysis, it is going to plot the output waveform on the screen and you can verify the output. This is the brief procedure about how to work with PSpice. Now, as I have told you, you must be ready at least by next week with the installation of PSpice. Those who have a laptop. Those who do not have a laptop, you are going to tell me the reason that you don't have a laptop. That we already know. But my suggestion would be, laptop becomes a very essential tool for you in future. For preparing your own project reports or for presentations or even for saving the resource materials for learning, laptop becomes necessary. So those who can afford to have a laptop, it is better to buy a laptop now itself, so that it will be easier for you in the teaching learning process also. Okay. But one problem with the students is, once you have a laptop, you will load it with all types of movies and you waste time that way also. If that is the intention, then don't buy laptop, because you are unnecessarily going to waste your parents' money. That should not be the intention. Once in a while you can have movies on the laptop and you can watch, but you should not use the laptop only for watching movies. There you have to be careful. But laptop will be useful even in future when you have a lot of documentations, especially for engineering education. Laptop will become highly useful. So those who can afford it, you can buy a good quality laptop and gradually you can start working with it, especially to learn engineering only, not for other purposes. Okay, those who already have a laptop, our suggestion or advice to you would be, those who are already having laptop, you will have to download PSpice and install. Will I be able to know how many of you are having laptop? There are now 19 students. How many of you are having laptop? Can you put yes or no in the chat box?
So could you send the link for install?
Linking for installment, there is nothing. You can directly search in Google about PSpice installation. It will take you to that particular website. It is quite easy. It is not complicated. If at all you find any problems during installation, then you let us know in the next class. Or you can put your issues in the Google class also. Otherwise, it is quite simple. Okay. Now, Rohit and Nidhi and Sukita, these three students have answered yes, sir. Now, there are 19 students, out of which only 3 have answered. What about remaining 16? They are not putting no also. What about the remaining 16 students? Okay, Sachin has put yes. Harshit has put no. Puneet has put no. Sagar has put yes. Yashwant has put no. Sai Vignesh has put no. Puneet M has put no. Fine. Rutesh has put no. Fine. Those who are not having, I will not force you, don't worry. But I have advised you already, it is better that you think about buying a laptop gradually in future if you can afford it. Otherwise, unnecessarily don't pressurize your parents. But it is a good idea to have a laptop. Otherwise, also when you come to the final year, you will need it. For all your project report work, you will need it. Even for your placement work, you will be needing it. Especially in final year, you will be needing laptop. For other years, somehow you can manage with the desktop if it is available at your home, or even when you come to college, here when we have desktop systems, you can keep working on them. That is no problem at all. But now these students who have told yes, sir. 1, 2, 3, 4, 5. Now 5 students have told yes. Means these 5 students who are having laptop, you can download and install the PSpice version. Student version is available. You can start working on it. From next class onwards, we will show you a demo here also in our class. Meanwhile, we expect that you keep working there at home as well. That will be a knowledge enrichment for you. Okay, so today's experiment is voltage multipliers using simulation. When we framed the syllabus for the AEC lab, I purposefully told the syllabus setters that these voltage multipliers, let it be simulation experiment only. In fact, earlier when we had a hardware lab, we did not have the voltage multiplier experiment at all. We purposefully added it to the syllabus. My intention was that the students should understand all the circuits which are utilized in the industries. Even though we are not teaching you in the theory class, it is easy. It need not be taught in the theory class exclusively. It is easy to understand its functionality, and they are used many times. Even your mobile phone charger contains a voltage doubler inside. Even in computer, sometimes we have voltage doublers. Even for a SIM card power supply, there is a voltage doubler inside the mobile phone. So it is better to understand the functionality of all these circuits. That was my intention when I insisted on putting this in the syllabus. And I told, let it be a simulation experiment only. What I wanted was, students should have the hardware experiments practice also. They should be exposed to the simulation tools in the second year itself. I am proud to say that when our university itself was not having simulation in the third semester, we in the autonomous program added simulation in the third semester lab. That's why I am proud to say. So we wanted that in the third semester itself, students should be exposed to the automation tools. So in the third semester, we added PSpice. In the fourth semester, anyhow, you have Xilinx. In the fifth semester, you have Cadence. And in the fourth semester, you will be exposed to one more software called MATLAB. And in the sixth semester, when you come, you will be exposed to microcontroller architecture, and you will have such programming lab there using Cortex M3 boards, using the embedded boards. So gradually, in that way, we had planned our syllabus. So coming back to multipliers now. This I especially put it into simulation program only. The reason is, if at all you connect the capacitors in the reverse way, in the hardware experiment, there are chances that the electrolytic capacitor will burst out, which can be dangerous in the lab. Now, when you perform in simulation, nothing is going to happen because it is only a model. There is no physical device there. So in the computer, nothing of that thing is going to happen. It is quite safe. That is why we had put this voltage multiplier in the simulation experiment itself. Now today we are going to see doublers, triplers and quadruplers. Voltage doublers means all these circuits are AC input and DC output. Let me write a block diagram. Now input is AC, output is DC. This is the symbol for DC. Okay. Whether it is voltage doubler or voltage tripler or voltage quadrupler, input is AC, output is DC. In the sense, let us say you will have a 10 volts peak to peak signal. Let us say this is +5 and this is -5. Total, it is a 10 volts peak to peak signal. Now, this signal, AC signal, is converted into DC inside, and it is either doubled or tripled or quadrupled. Means here the peak voltage is 5. Even if it is -5, if you go for a full wave doubler, it will become +5 only. We can go for a half wave doubler also, where the negative cycle is ignored completely. We have a half wave doubler, we have a full wave doubler also. So that is only a rectification part. Now this 5 volts, in case of a doubler, it can become 10. In case of a tripler, it can become 15. In case of a quadrupler, it can become 20. Now AC is the input, DC is the output. How it becomes double, we will see later on. Don't worry. Now, why I told you that even in the mobile phone, you will have a doubler? There, the battery voltage is only 3.6 volts. Whereas there is a vibrator motor. There are some vibrator motors which require larger voltage. And that is one reason. One more reason is, Sometimes the power supply to the CPU will be 0.9 volts, whereas SIM card requires 1.8 volts. In such a case, they can use doublers there also. Even in your mobile phone charger, there is a doubler circuitry. But the mobile phone charger circuit is a very complicated circuit. We will not discuss it here. That is the SMPS circuit, switch mode power supply circuit. But you can see that input is AC and output is DC. That is how these doublers are working. DC to DC doubler is not there. Remember, DC to DC doubler is not there. It is only AC to DC always. DC to DC doubler is not easy to construct. It is not so easy. Fine, let me continue now. Study and test voltage multiplier circuits, voltage doubler, voltage tripler, voltage quadrupler by simulation using either multisim or PSpice. We are using PSpice. There is another software called multisim. Multisim means multiple simulations. It has got multiple options for simulation. That's why it is called as multisim. You can use PSpice also, you can use multisim also. It is up to you. But in our lab, we are predominantly using PSpice only. So the software requirement is OrCAD PSpice version 9.1. OrCAD was the company which had introduced PSpice. Now OrCAD is also purchased by a company called Cadence. So OrCAD has been integrated into Cadence software now. A brief theory. The voltage multiplier is an electronic circuit that delivers the output voltage whose amplitude is 2, 3 or more times greater than the amplitude of the input voltage. The input voltage is AC. The voltage multiplier is an electronic circuit that converts the low AC voltage into high DC voltage, or the voltage multiplier is a AC to DC converter made up of diodes and capacitors that produce a high voltage DC output from a low voltage AC input. Applications. The voltage multipliers are used in cathode ray tubes, in traveling wave tubes, in laser systems, in X-ray systems, LCD backlighting, high voltage power supplies, oscilloscopes, particle accelerators, ion pumps, and copier machines. Photocopier machines also use voltage multipliers, because all these equipments at one point, for some of their printing jobs or for their display jobs, they require a high voltage. But input is only 220 volts AC to them. Cathode ray tube requires more than 1000 volts inside for heating up the electron gun. Now, using 220 volts only, 1000 volts DC is produced. 220 volts is the input AC. 1000 volts DC is produced inside the cathode ray tube. That's the same case with all other examples given here, including the copier machines also. Copier machines, you have a drum there, and on the drum the paper rolls. For moving the drum, high voltage is required. But the input to the copier machine is only 220 volts AC. So a higher voltage is produced inside the photocopying machine for the movement of the drum. Now, let me come to the circuit. Initially, we will see the half wave voltage multiplier circuit. You can see here, this is now a PSpice version itself. It is a PSpice snapshot only, where you will pick up a diode and you will place 4 diodes one after the other here on the screen, and you will pick up a capacitor, again you will place 4 capacitors here on the screen, and then you will connect all of them through these wires. And then at the input, you will give this AC source, AC signal source. Its frequency is specified as 1 kilohertz, amplitude is 5 volts. That means it is a 10 volts peak to peak signal now, plus 5 volts up and minus 5 volts down. V off is 0, off means offset, offset means DC. This is pure AC, it does not have any DC component. That is the meaning here. Now, you place this AC source here, then connect a capacitor here, connect a diode like this, again one more capacitor, connect a diode like this, again one more capacitor, connect a diode like this, one more capacitor, connect a diode like this. You should be careful when you make connections. See, here they have shorted these Actually, because this is a snapshot or a screenshot, there is no problem. Otherwise, this circuit here, it cannot be simulated because the capacitor is shorted, you can see here. So you should be careful. When you pass wires, you should not pass wires on the components. Automatically, these 2 points will be connected. You can see here, they are connected, which is not the case with this capacitor or with this capacitor or with this capacitor. There was a mistake here when they took this snapshot. Anyway, this is only a manual error. When you actually simulate, you will find out and you will correct it. Now, we are using a capacitor 1000 picofarad. 1000 picofarad means it is 1 nanofarad. 1 nanofarad here, one more 1 nanofarad here, 1 nanofarad here, one more 1 nanofarad here. Now, this is a half-wave voltage multiplier. You can see there is a single diode here, one more single diode here this way. Now, let me explain briefly the working of this. Let us say the positive cycle is coming now. When the positive cycle is coming, this diode is now conducting in the positive cycle. In the positive cycle, this diode is conducting. Capacitor passes AC. And at that time, this is not conducting. And at that time, again the capacitor passes AC. So this diode is conducting. At that time, this is not conducting. Okay. So D1 and D3 are conducting in the positive cycle and capacitor passes AC. Whereas in the negative cycle, D2 and D4 are conducting. At that time, C2 and C4 are going to pass AC. But when D1 is conducting, you can see here, when D1 is conducting, at that time, what will happen to C2? When D2 is not conducting. D2 is not conducting, D1 is conducting. So signal is going like this. And what will be the voltage at this point? See, capacitor passes AC, D1 is conducting. But at that time, C2 is not passing AC because D2 is not conducting. Okay, when D2 is not conducting, D1 is conducting. In which direction the capacitor will get charged? Can anybody tell? Can anybody tell? Okay. You can see this ground here. Actually, in this circuit, ground is also not necessary. Here they have put a ground. Otherwise, when you actually simulate the circuit, now, at this point, you will get double the voltage. And at this point, you will get triple the voltage. At this point, you will get quadruple the voltage. At different points, you can place the probe. When you run a simulation, you can place probes everywhere. Wherever they are showing these values, these are all actually probe points. So you can place probes there. And when you place probes, when you simulate, the probe is going to show you the output. Now, here you will have a double because the capacitor's one end is connected to the diode and the capacitor gets charged by plus 5 volts. Now, when this capacitor is not, let us say when this D1 is not conducting, then C1 gets charged. Because when D2 was not conducting, C2 was charged. Accordingly, you can say when C1 is charged to 5 volts, C2 gets charged to 10 volts, C5 gets charged to 15 volts, C4 gets charged to, 5, here 10, 15 and 20. That means here you will get double voltage, here you will get triple voltage, here you will get quadruple voltage. Now let me stop annotating. This is a half-wave voltage multiplier where you will have doubler, tripler and quadrupler all in one circuit. Wherever you want to take whichever one, you can take it. But it is half-wave because in the negative cycle, D1 is not conducting. Only in the positive cycle, D1 is conducting. D2 is conducting in the negative cycle. But at that time, because of C1 already being biased or charged. When D1 was conducting, D2 was not conducting. C1 retains that 5 volts. Now the question is, in the positive cycle, C1 is passing. In the positive cycle, when C1 is passing like this, in the negative cycle, how it can retain the charge? Will it not discharge? Is the question. In the positive cycle, D1 is conducting and C1 is charging. Okay. Now in the negative cycle, will it not discharge? Because in the negative cycle, D1 is not conducting, but D2 is conducting at that time. When D2 is conducting, will the capacitor discharge or not? Is the question. Can anybody answer?
Sir,
Yeah. It will discharge only if there's a discharge path, right? But where is the discharge path here? There is no discharge path. Discharge path means there must be a load connected. For example, let us say we connect one resistor here. Only if we connect a resistor here, then the capacitor will discharge. Now, if we have not connected a resistor at all, it will retain the charge. C1 will retain the charge. If there is no load connected, C1 will retain the charge. Why? This is AC. See, one cycle, positive cycle, D1 conducts. Negative cycle, D1 does not conduct. Again, positive cycle, again D1 conducts. Negative cycle, D1 does not conduct. So, cycle after cycle, signal is coming because the frequency is 1 kilohertz here. Cycle after cycle, when the signal is coming, capacitor will never discharge. It will retain the voltage. It will discharge provided there is a load connected. Now, there is no load connected here. If the load connected is there, definitely capacitor will discharge. Okay. What they do in the real-time application is, the load will be of a much larger value. For example, let us say I connect a resistance which is of 10 kilo ohms. Now also capacitor will discharge, but the discharge rate of the capacitor is much lesser because of the time constant tau, R into C. 10 kilo ohms, very high resistance value. So current is very less here. So before the capacitor discharges, another cycle comes here, right? See, first cycle, second cycle keeps on coming, right? So capacitor charges again in the next cycle. That way, the capacitors will never discharge. When they do not discharge, they will retain the value. So here if it is 5 volts, here it is 10 volts, here it is 15 volts, here it is 20 volts. That way, doubler, tripler and quadrupler. All the four are working, all the three are working together in a single circuit. This is a half-wave voltage multiplier circuit. Any questions here? If there are no questions, I will proceed to the next circuit. Okay, there are no questions. Tell me, I am unable to hear you. Can you tell me again?
sir, won't there be like a small amount of discharge from the capacitors?
It will be. Later on in the simulation curve, I will show you. There will be a slight amount of discharge. And there will be a slight drop across diode also. So there will be a 0.7 volts drop across all these diodes. So we will not get exactly double. That means 5 volts means we will not get 10 volts. But we will get somewhere nearer to 10 volts. There will be a slight discharge, but the point is, we have purposely kept the frequency high here. See, frequency is 1 kilohertz. That is to prevent the discharge only. Because it has to discharge in the other cycle, right? Let us say in the positive cycle it is getting charged, in the negative cycle it has to discharge, right? But before that, again one more positive cycle comes. That way, if the frequency is large, then the discharge is also lesser. Any other questions? Okay, let me proceed to the next circuit. Now this is full wave voltage doubler. Now this is a full wave voltage doubler. You can see here, in the positive cycle, this will conduct, this diode will conduct, and you can see the ground is connected here. When ground is connected here, current flow is in this direction. Now in the negative cycle, what happens is, this D9 is off. In the negative cycle, even the capacitor passes AC, D9 is off. So in the negative cycle, D8 is on, because this becomes plus then. When this becomes plus and, sorry, this becomes minus, this becomes plus. So current flows in this direction now. In the negative cycle, sorry, in the positive cycle, D9 conducts. In the negative cycle, D8 conducts. So now you can see, in the positive cycle, D8 is off. In the negative cycle, D9 is off. Ground is connected here in the middle. And this is, there is no junction. You can see there is no junction. This is not a connection. Connection is here. There is no connection here. So, in the positive cycle, when D9 is conducting, and at that time this capacitor gets charged to 5 volts, let us say. If the input is 5 volts peak or 10 volts peak to peak, we have given the amplitude here as 5 volts. So, this capacitor charges to 5 volts, C1. Now, C1 will not discharge in the negative cycle. Why? D9 is reverse biased. And C1 will not discharge also. Why? Load is not connected. You cannot see any resistance here. If there is a resistance here, then only it discharges. Otherwise, it remains charged. Now you can see, in the other cycle, D9 is conducting. When D9 is conducting, C2 is getting charged now. When C2 is getting charged, now the net voltage across these two capacitors is totally double. In one cycle, C1 gets charged. In the other cycle, C2 gets charged. Now, together when we take output from here to here, we have, see, you can see the probes connected here. V plus and V minus are connected here. So when we take output in between these two, each capacitor retains the charge in the other cycle. So totally we get 10 volts, and this 10 volts full wave. Why? Both cycles are made use of now. So there will not be any ripple. You would have seen that in a half wave rectifier there will be a ripple like this. There will be a ripple. But in a full wave rectifier, again one more cycle comes, there will be a very less ripple here. Full wave rectifier will not have much ripple when compared to the half wave rectifier. That is because the other cycle also is utilized. So this way, now this is a full wave voltage doubler. Now this is a straightforward easy circuit. I don't think there are any questions here. Do you have any questions? And you can see the diode which we use is D1N4002. 1N is normally the notation for diodes. Americans use this convention. 2N is the notation for transistors with the American convention. And at 4001, 4002, 4003, that way it goes on up to 4007, there are numbers. Now that 4007 diode can withstand 1000 volts PIV, peak inverse voltage. In the reverse bias, it can withstand 1000 volts. But here we are giving only 5 volts, right? So we are using 1N4002. This diode can withstand 200 volts in the reverse direction. But we are giving only 5 volts here. So it does not matter. So if there are any questions, you can ask me. Otherwise, this is a very straightforward circuit. There is nothing much to understand it here. It is very simple to understand. This is a full wave voltage doubler. Let me move on to voltage tripler. Here you compare the earlier circuit with this circuit. Now you can see in the positive cycle, D1 is conducting. In the negative cycle, D4 is conducting. And in the negative cycle, D5 is conducting. In the positive cycle, D1 is conducting. In the negative cycle, D4 is conducting. But at the same time, in the negative cycle, D5 is conducting. So what happens here is, in the negative cycle, when D4 is conducting, this gets charged to 5 volts. Okay, this gets charged to 5 volts. But in the positive cycle, initially, when D1 was conducting, C1 gets charged to 5 volts. And when D5 is conducting here, you can see, when D5 is conducting in this direction in the negative cycle, at this point, there will be 5 volts. C1 will retain this 5 volts. And D1's one end is at 5 volts. Now in the positive cycle, when D1 is conducting, C1 is passing AC, but that AC is having a superimposed 5 volts DC. You can see, here it is a pure AC coming, but when it comes here, at the anode of D1, this AC will have 5 volts DC added because that DC was stored by C1 itself. So D1 conducts with 5 volts DC also along with that AC. AC is again 5 volts. So the C4 gets charged to 10 volts because of this plus 5 volts here. Now you can see when we take output here and here, there are two probes here. C3 is charged to 5 volts and C4 is charged to 10 volts. Totally we have 15 volts. Ignoring the diode drops. Across diode, there can be some 0.7 volts drop. Ignoring the diode drop, we can ideally say we have 15 volts. I hope it is clear to the students. This is a typical circuit where for the negative cycle we have only, for the positive cycle we have only one diode conducting. During the negative cycle, we have the lower one also conducting. We have one more upper one connection. That is the brilliant circuit arrangement here, due to which now this circuit is a voltage tripler. I hope you have understood this. Because C1 retains 5 volts because of D5. And when D1 conducts along with the AC plus 5, there will be C1's charge plus 5. Total it will become 10 volts. So C4's upper plate is charged to 10 volts. But C4's bottom plate is connected to C3. C3 is also charged to 5 volts during the negative cycle. So due to which totally we have 15 volts. Coming to the last circuit, that is voltage quadrupler. Let me slightly zoom out. Okay, this is voltage quadrupler. This is the extension of voltage tripler itself. You can easily understand this. In the positive cycle, D1 conducts. Okay. In the positive cycle, when D1 conducts, and in the negative cycle, D5 conducts. Now in the negative cycle, D4 conducts, but in the positive cycle, D3 conducts. You can see this. In the positive cycle, you can see a connection here. There is no connection here. Here there is no connection. Here there is a connection. So let me use different colors. In the positive cycle, D1 conducts. In the positive cycle, D3 conducts. Now, in the negative cycle, D4 conducts. And in the negative cycle, D5 conducts. Now, because of this typical arrangement, what happens here? Because of this typical arrangement, here we will have 5 volts. And here we will have 5 volts. Now, because we have 5 volts here, here we will have 10 volts. Because we have 5 volts here, Here we will have 10 volts. As I told you earlier, when AC is coming this side, if this capacitor is charged, along with the AC, there is a superimposition of 5 volts DC because of the previous cycle when D5 was conducting. So that 5 volts along with this 5 volts is going to become 10 volts. Similarly, in the other cycle, when there is this 5 volts, that 5 volts is going to become here 10 volts. So when we take the output from C4's plus and C3's minus, we take the output here and here. 10 plus 10, we are going to get totally 20 volts. That way, this is a full wave voltage quadrupler. Why full wave? Because both cycles are taken care of. Positive cycle as well as negative cycles are taken care of. At both cycles, diodes are conducting. 2 diodes will be conducting, 2 diodes will be off. That way, this is a voltage quadrupler. And with that, I have completed the circuit descriptions of voltage doubler, half wave voltage doubler, then full wave voltage doubler, full wave tripler, full wave quadrupler. Let us see the simulation results. Now you can see the voltage doubler's output. You can see that blue line, whatever you see as blue, is the AC waveform, which we have given at the input. We have given it 1 kilohertz, that is why it is coming so nearby. Now, input is AC, you can see this pink line, pink or violet line. That violet line is somewhere near 10 volts. You can see this is 5 volts, this is 10 volts. It is a 5 volts peak to peak, plus 5 and minus 5 is the input. Whereas output is nearer to 10 volts, somewhere about 9.5 volts. Now, what is this 9.5 volts? There is a drop. Actually, at 9.5, it is around 9.3 volts. Because there is a 0.7 volts drop in the case of the voltage doubler, because there is a 1 diode conduction there. Because of which 0.7 volts drop is there, remaining 9.3 volts is coming here. This is voltage doubler. These are the simulation settings for voltage doubler, which you can actually do on your own when you simulate this circuit. Now coming to voltage tripler. Ideally, we were supposed to get 15 volts, but we are getting somewhere near to 13 point something. There are 2 diode drops here now. In the case of a voltage tripler, there are 2 diodes. So due to which 0.7 plus 0.7, 1.4. Now 15 minus 1.4 is around 14.6. So you can see here around 14.6 volts is the output here out of the voltage tripler. Whereas the input you can see that cyan colored, we call it as cyan only, no, C-Y-A-N, cyan colored, or do we say cyan? Which color? I don't know how to pronounce this word. Cyan or cyan, I don't know. In that way, this color is input and this violet color is output. You can see 14.6 volts output. Lastly, coming to voltage quadrupler, we were supposed to get 20 volts output. You can see the input here at the cyan color or cyan colored waveform. Now 5 into 4 we must have got 20 volts, but now we have 4 diodes. We have 4 diode drops, and because of these 4 diode drops, now here we don't get exactly 20 volts. Even though it is 4 diode drops, we are getting 10, 12, 14, 16, 18 volts. So approximately 18 volts we are getting. That means those diodes 0.7 into 4. We must have had around 2.8 volts drop. Now in this case, when 2 diodes are conducting, other 2 diodes are off. When other 2 diodes are conducting, other 2 diodes are off. So actually it is only 2 diodes drop there. So because of 2 diode drops, 0.7 into 2, 1.4. There must be more drops across these diodes. Somehow we are getting around 18 volts instead of 20 volts. So with this, we have come to the end of today's experiment. Do you have any questions?
Sir, can we multiply the voltage by 10 times, 20 times, like that? Is that possible?
The same voltage quadrupler principle, you will have to increase further. See, you have this voltage quadrupler, right? Now you will have to have a duplication again here. Means the same circuit connect one more stage. It will become 8 times. That way you can. Any number of multiplication is possible. As long as you do not connect the load. Load should be very less here. In the sense, we cannot connect a heavy load to the circuitry. If you have to connect a heavy load to the circuitry, the value of the capacitor must be increased. We are now using only 1 nanofarad here. If it is in microfarad, it can supply current also that way. It will remain charged. So it is possible. Any other questions? Okay, students, now your job is you will have to note down the observation book for today and you will have to upload in the Google class. I'll ask Prithviraj sir to create one assignment in the Google class and you will have to upload today's observation because we have official instruction that we should not stop the meeting here now. We should continue because the lab is actually for 3-hour session. So this meeting will be on. I will only be stopping the recording here because it will remain empty, means there is no use in recording. I will be stopping the recording. I will be sharing the recording in the Google class also. But now you will have to write the observation book and you will have to upload into the Google class. Meeting will be on. Okay. Okay, Prithviraj sir.
Yes, sir.
Prithviraj sir, you want to tell something?
No, sir, nothing like that. I think the manual is there in the Google Classroom. They
Okay.
can, sir, today they are going to write this experiment, sir, or something else.
Today let them write today's observation book only.
Okay, sir, fine.
Whatever, at least the circuit diagram, whatever they have seen today, let
Yes,
them write it and let them upload the PDF to the Google class.
Yes, sir. Yeah.
Because this observation book also carries marks.
Yes, sir.
Yeah, students, attendance carries 1 mark, observation book carries 1 mark, record carries 1 mark. So it is mandated for you to write observation book for today's experiment and upload it to the Google class because the class is actually from 1:50 till 4:50. It is supposed to be for 3 hours. So this meeting will be on. I will not be ending the meeting. Only thing is I will be stopping the recording just to just not to have that empty space there in the recording of the video. Okay, I am stopping the recording, but meeting will be on.